Okay, welcome to Physical Science Module 15, Part 2. We're covering the second part of Module 15 today. As usual, you should have your book handy for this class, so if you don't have it, stop the video and come back. Also, as usual, if you have any questions, you can contact me at Mr. C at mrcscience.com. Oops, wrong tool. As you notice, I now have a stylus and a tablet, so now we don't have to watch me write on the whiteboard anymore. I can write right on the computer here, so hopefully things will be a little bit clearer. That being said, let's move on. Okay, so what we're going to do is, last week we talked about light and reflection, or light bouncing off of objects. And we learned that the angle of incidence equals the angle of reflection. Today we're going to talk about light passing through substances. Okay, on your book, go ahead and turn to page, oops, get the right tool, page 379. And we're going to talk about light passing through substances. So at the bottom of page 379 are two things in bold. You'll need to know these for the test, although they might be a little confusing right now. When light refracts into a substance in which it must slow down, the light ray will bend toward the line perpendicular to the surface it strikes. Okay, this is a little confusing. Let's talk about this. So let's say we got a light ray and it's traveling, and we want to pass it through some glass. So let's play here a little bit. Let's grab a light blue for our glass. Let's set that. Okay. So we got a chunk of glass. Oops. Okay, there's our chunk of glass. Okay, now what we've got is we've got a light ray that, Control Z. Sorry, getting used to my tablet a little bit. Okay, so we've got a light ray that travels towards the glass. So there we go. We got our light ray travels towards the glass. So what happens when it hits the glass? Well, what happens is that light travels at different speeds in different substances. You saw that we talked about this last week, that the denser the substance is, the slower it goes, right? So glass is more dense than air. So when it hits the glass, it's going to slow down. And I'll explain this to you a little bit, but what they want to say is they say when it hits something that's more dense or where it slows down, light will bend towards the perpendicular. Okay, so what's the perpendicular? Let's talk about the perpendicular here. So let's grab, no, that's not what I want. Oh well. Okay, that'll just draw it. Okay, so light hits the substance. Perpendicular is a 90-degree angle to our point here. So if I draw a little line, we got a line going 90 degrees perpendicular. So this is what's called a right angle, or 90-degree angle. So when light hits it and it goes into a substance that is less or more dense than the other substance, it will slow down, in which case it will bend towards the perpendicular. So what we got here is we got our original angle compared to the perpendicular right here, and that will be greater than the angle right here as the light bends towards the perpendicular. So why does this happen? Well, you can look at it this way. It's kind of like driving a car on a road. Light's traveling along a nice line here, and let's say light comes in waves, so it's got its crests and its troughs as it goes. Now it hits a substance with more dense than itself. So as it hits that substance, the light, the part that hits it's going to drag. If it's denser, it's going to start dragging. So it's going to drag, and that drag is going to cause it to change directions. It's going to bend towards the perpendicular. It's kind of like driving your car down the road, and if one tire goes off the side and grabs the edge, the gravel on the edge, it's a little more friction, it'll try to drag the car that direction. So this is what happens. This is why light bends towards the perpendicular when it hits a more dense substance. So what's going to happen then, I'm going to get rid of that, is so once light comes back out here, it's going to go from a more dense substance into a less dense substance back into the air, and it's going to bend away from the perpendicular. Or since it's the same substance, it should have the same angle as the original one. So that makes sense. So the second part of that thing on the bottom of page 379, when light refracts into a substance in which it speeds up, the light ray will bend away from the perpendicular. So it's going faster here, it hits a spot where it's slower, it's going to bend towards the perpendicular, then it hits a spot where it's faster, it's going to bend away from the perpendicular. I hope that makes some sense to you. So if you look on page 380, we've got a flashlight that is shining into a beaker. So here, let's just kind of draw this here quick. Delete. Okay, so if we've got our beaker, that's a really bad beaker, and in the beaker is some water. The light ray hits the beaker, the water is more dense, we're not going to worry about the glass at this point, it's so thin it doesn't matter. It's going to bend towards the perpendicular. Then when the light goes back into the air, it's going to bend back out away from the perpendicular. What's also going to happen is some of the light will reflect, in which case the angle of incidence equals the angle of reflection. Same thing when it hits this side, some light will reflect. Again, the angle of incidence equals the angle of reflection. And you can see that laid out right there in that diagram. Looks better than what I've just drawn here, but it gives you a good idea. There's an experiment here called the magic quarter. You can try it if you want. If you look just towards the edge of the bowl where you can barely see, if you look on the bottom of page 381, the girl looks into the bowl, she can barely see the quarter. When she puts water in the bowl, the quarter appears to have changed directions. Now, they don't do a great job at explaining why this happens, but they could have here. So what she sees is she sees a virtual image. So if we go here, let's try our bowl. And our water. Here's our coin at the bottom of the bowl. So here's the eyeball looking down. So what happens is as the light wave bounces off the coin, so it comes in, light wave comes in, refracts down, bounces off the quarter, refracts back out again, and your eye. So what happens is, to you, if you draw a straight line from the light in your eye down here, it appears that the quarter is over here. That's called a virtual image. And so what you see is that's not a very good eyeball. What you see is a virtual image of where it is. So that's like people that spearfish, or bowfish. If they try to throw directly at the image of the fish, say this were a fish, terrible looking fish. Okay, and they shot at the fish, they would miss it because the fish is really here. So that explains how refraction comes into play there, so you can read a little bit about that. What's interesting is different types of light refract differently. If you turn to page 382, you'll see making a rainbow at the bottom. So what happens is this is a little water droplet in the air, and light, which is all colors of light, all visible colors, when it hits the water, it slows down, it refracts, it bends towards the perpendicular. When that happens, different colors of light refract differently. So they start separating, and then it refracts again. When it reflects and refracts again, it comes back out. But this separates out the light so that you can see the different colors. The reason for that is different color lights have different frequency. Do you remember what frequency is? Oops, wrong one. Frequency equals what? It equals hertz per second, so it is wavelength, or I don't remember. Frequency equals, frequency is basically has to do with wavelengths. How many wavelengths go by per second? It's got a short frequency. It's got a lot of wavelengths going by per second. It's got a longer frequency. It's got less wavelengths going by per second. Speed of light is the same for both frequencies. So in this one, if this was 1 second, you'd have 1, 2, 3, 4, 5 wavelengths, or frequency of 5 per second, or 5 hertz. This one's got 1 and about a half, so this one has a 1.5 per second, or 1.5 hertz. So because of the wavelength, they will bend slightly differently, and that will change the colors for you. Okay, so let's go to where refraction is actually relatively useful, other than looking at quarters at the bottom of the bowl. Refraction is useful if you have bad eyesight. You need to adjust your focus on your retina. So if you look on the bottom of page 383, you will see a lens. This is what most people think of a lens. Oops. Cancel. Not sure what I just did. Okay. We got a lens normally looks like this. So what happens is light rays come into the lens. You're looking at something. And what happens is the light ends up focusing at a focal point right here. I used this before. If you used a magnifying glass to light paper stuff on fire, the light from the sun is coming from a relatively straight direction since it's so far away, and it focuses. You can use this to adjust the focus on your back of your retina. So what really happens in the lens, if we take a close-up look, so here's a close-up look at the lens. So as the light ray comes in, it will bend towards the perpendicular. Say, well, what's the perpendicular on a rounded lens? Well, it's called the tangent here, or the what's that? It's an arc. But basically, you find the perpendicular where the light hits. So because the lens is more dense than the air, it's going to bend towards the perpendicular. So it's going to do a little bending down more towards the perpendicular. Same thing will happen on the other side. It'll bend in, and that's where you get your change in refraction, how you can find your focal length. When we get to, go ahead and turn to page 384. Here's a better picture of this. But this is called a focal point. Your lens in your eye attempts to make this focal point, or actually right near there, appear on the retina on the back of your eye, so that you can see what's around you. Okay, this is called a converging lens. That's because the light converges to a single point. If you look at the next page, figure 15.10, you'll see what's called a diverging lens. This is called a diverging lens because the light bends away from each other. Diverging lenses, this is over. You usually won't see a lens with that much of an arc to it, but diverging lens, kind of like the converging lens, the light comes straight in, but now it ends up bending out. It expands. And if you were to look at a diverging lens, you'd want to look from this side, and the image would appear virtually inside the lens that way. So you can use a diverging lens to make things look bigger. So, okay. They're called converging lens. This is called convex. So if you look at the center, anything that bends towards this, oh, that's cool, I drew a circle. I wonder if I could do that again. Anything that bends towards the center is called convex. Anything that bends away from the center So this is the center now. It's bending away from it. It is called concave. So, and a converging lens has a convex lens or bends to it. A diverging lens has concave bends to it. Okay, I'll go ahead and turn to page 386. So in here you see a picture of the human eye. The human eye has a lens in the front. Actually, what's kind of interesting is it's got a couple lensing actions going on. You get into anatomy and physiology, you'll learn a little bit more that the cornea actually does some lensing action as well. But so you'll see. Here, let's just draw it. Oops. Wow, here's our cornea. Here's our eye. Here's our eye. Here's the nerve coming off the back. Here's the lens. Oh, that's a really bad looking lens. There we go. There's the lens. Lens has some muscles that pull on it to change the shape of it a little bit. It's got the iris to control the amount of light going through. But as light comes in, it will bend through the cornea, it will bend through the lens, and it will focus on the back where the retina is. They show the retina up here, but you get the general idea. In the retina are things called rods and cones. They're called rods and cones because they look kind of rod-shaped or cone-shaped. These sense color and black and white, which would be contrast. So light hitting on them can do an interesting thing on how just complex that is later on. But that's effectively how your light works. So your eye uses a converging lens to focus the image on the back of your retina so that the rods and cones can sense it and transport an image of it to your brain. Okay, so how we perceive color. So here, let's try a little experiment. We can actually do this experiment on here. So if I get rid of you, delete, let's grab, here. Actually, it can be that. So let's make a bright red. Don't care about the stroke. Okay, so let's draw a box. Okay, it's bright red. I'm going to click off it so you don't see all the answers. Okay, what I want you to do is I want to stare at this box. It doesn't matter if you blink. You can blink normally. Just keep staring. In fact, the easiest thing is to stare right at the center dot right in the box if I hover over it. So while you're staring at it, what's happening is the rods or the cones in your eye, the ones that go for color red, are saying, oh, I see red, I see red, I see red, and they're going, oh, I'm getting tired. That's a lot of information. It requires a lot of energy. So they go, oh, I'm exhausted. I'm shutting down. So once they've shut down, what's happened is the rest of your brain's saying, oh, I know it's still red there. You haven't looked anywhere, so I'm just going to keep red there. So now when I say go, I want you to do this. So ready, set, look right here. What do you see? You should see kind of a blue-green, or cyan, or I'm not sure what color it's called actually, a blue color. So what happens is in your eye there are 3 different types of cones that affect color. So there's red. Oops. There's red, there's green, and there's blue. Red, green, blue. These 3 cones make up all the colors that you can see. If you go ahead and turn in your book to, we're going to jump ahead to page 391. This is a color wheel based off of light. You're familiar with one on 390 based off of pigments. So if you take red and blue and put them together, or no, this is added. No, we want 390. So if we take red and blue light and put them together, we get magenta. Now what we did is we were seeing white light right in the center, and that means all 3 colors, red, green, and blue, all go together. They combine together to get white. If we suddenly remove the red, so when we looked over, the red was still tired, the red cones were still tired, they couldn't turn back on, but the blue and green said, oh, I see that, I see white, so they turned on. And if you look at blue and green make together, they make cyan. That was the color we saw. So let's do a little experiment. What happens if we turn the blue one off? We should just see red and green when we look at the white, and we should see yellow, right? So let's do this. Let's change our color. Let's go change our color to blue. There we go. Okay, so once again, I want you to stare at the blue. Now this time what's happening is those blue cones are getting overwhelmed. They're saying, I can only do this for so long. That's why I like when you see a flash from a camera, you see spots, because those rods and cones get overworked. So right now your blues are all shutting down because they've had enough. And so now when we look over on the right, we're going to see yellow. Ready, set, go. You should see yellow. I see yellow. I see a little bit of red too. Part of that could be the fact that maybe this blue isn't a true blue. But so same thing. So if we did it with green and shut down our blue and our red, what color do you think you'd see? You'd see magenta. So now that's for additive colors. Subtractive colors, that's more what we're used to. Subtractive colors are where we take paints, and like a yellow paint and a cyan paint, or a blue paint, and we make a green paint. You take a magenta and a yellow, put them together, you make a red. If we put all the colors together, we make a black. So that hopefully makes some sense. There will be some colors on types of lights shown. So why we see blue, let's talk real quick. Why we see the blue color is if we shine light on there, white light on there, everything is absorbed except for blue. Alright, yep. So blue is reflected back at us, everything else is absorbed. That's why we see it. So if we took and shone a blue light on blue, we'd see it blue. If we took a yellow light made out of green and red and shone it on blue, we would get no blue back, and we would actually see a black because we get no light reflecting back to us. So that's how light interacts with that as well. So it's kind of interesting. Go ahead and read it. If you have any questions, don't be afraid to email me again at Mr. C. I won't write it. Mr. C at MrCScience.com. Email me any questions you got on this, and hopefully that'll get you through your study guide and your test. We'll connect later then. Thank you.